Hello and good morning to all of you. I welcome you again to the lecture 4 of Unit 1 of double EC 2710 oblique triple EC 2710 circuit theory. The topic for today's discussion is capacitor. So, in the last class, we have gone through the inductor. Okay, so as you know, that we have gone through in the detail the working of inductor. Okay, we have also gone through the some numericals over the inductance, and in this picture, which is a circuit which is built by my student, you can see that these are represented by L1, L2 and L3. In the last class I told you that these are all inductances. Similarly, you can see the circular, you can see the top view of the capacitors. So capacitors, I pre-assume that maybe you have seen somewhere or you may not also have seen it. So we will go through one by one what is the basic concepts of capacitors, okay, why they are used in electrical engineering, and what is the significance of capacitor in our electrical circuit in the various applications where they are used. So you see the capacitors and inductors are the most used elements in our passive electrical circuits. So uh, capacitors are generally used for maintaining a constant voltage. That is very famous about them, and that is also a energy storage element. That means the energy stored is the half CV square. That you already know. So all these references I have for your help, so that when you open book, you can get through the concepts. I have taken it from Sadiku, the reference book I have already mentioned. So as you can see, this is a very famous diagram of a parallel plate capacitor, which you have also gone through in your 12th standard, which is a representation showing that these lines are these plates are showing the positive and negative sides of a capacitor. That means this and this. So basically, what is a capacitor? Capacitor consists of two conducting plates separated by an insulator. So the word important here is that it is having two conducting plates which is separated by an insulator. So this is in between. You will find that there can be a dielectric. I am writing it like this. That means this capacitor will have two conducting plates, okay, and the material in between them will be the dielectric. So stronger will be the dielectric, stronger will be the strength of the charge holding capacity of capacitance. So as you can see from this expression that Q is equal to CV, that means the charge which is stored by a capacitor, or the voltage, if you write it in terms of voltage, so V will be equal to Q by C. Okay, so the greater amount of voltage will be impressed upon the terminals if the charge is there. That means if the plates are holding greater amount of charge, then a voltage will be impressed upon the terminal. So if you connect a voltmeter, you will find that there is voltage across the capacitor. Okay, so the dielectric, which is its relative uh, permittivity is represented by epsilon r, and if it is only air, then we represent it as like epsilon naught, and the multiplication of both these is the epsilon. So capacitance is the ratio of charge on one plate of a capacitor. Obviously whatever charge is on this plate, similarly is the charge on this plate. On the one plate of the capacitor, the voltage difference between the two plates. So the V is the voltage difference which you get at the terminals, divided by the capacitance, is the ratio of charge on the plate, that is Q, divided by the voltage across the terminal, so that you will get C. So usually 1 farad is 1 coulomb per volt. Okay, so the practical unit of capacitance, you can say, is not farad, but it is microfarad, or rarely we use capacitors of millifarad range. Usually in laboratory, the microfarad capacitance is enough. But that doesn't mean that capacitor is a perfect device. It doesn't have a resistance. Every capacitor which is there should have some amount of resistance. That is known as the parasitic resistance, also known as ESR. In some books, you will find it is written as ESR for the case of AC. If the capacitor is used for AC case, what is ESR? Equivalent series resistance. That means you will find equivalent series resistance with a capacitor. And similarly, in some books for DC, they write it DCR, that is DC resistance of a capacitor when it is used at DC applications. Okay, so all these expressions are famous expressions. You know that unit of capacitance is farad in honor of English physicist Michael Faraday. From equation, we can have this conclusion. Okay, so capacitors are commercially available in different values from picofarad to microfarad. They have, and there are two symbols for this. You see this symbol and this symbol. So in your books, you will find different symbols. For example, this is a one symbol. This is another symbol. Okay. So this symbol, which is very famously used in books, are in an indication of electrolytic capacitor. That means this capacitor. Where so capacitors can also be classified into two categories. That is polarized. They can either be polarized or they can be non-polarized. Okay. So you can use both of these terminologies, polarized and non-polarized. What do you mean by polarized? Polarized means that the one of the plates of the capacitor will always be at the greater potential than the other at every time. If the polarity of polarized capacitor is already fixed, that means if you are selecting this capacitor, then there will be a sign which will indicate this, that this plate will always be negative or less voltage as compared to the other plate that is positive. So all the electrolytic capacitors fall into the category of polarized. Okay, and polyester and ceramic capacitors, okay, which use a polyester or a ceramic as a dielectric material, can fall into the category of non-polarized capacitances. But you can see the most famous capacitors which we use in the laboratory are electrolytic capacitors, which are polarized capacitors and having a symbol like this, because they are having the highest permit permittivity and the capacitance is the highest one. Because C, as you know, so all these are different types of capacitances. Variable capacitances are also there, but not very famous. Usually in all circuits, 95 to 98% circuits, we use fixed capacitors. Very rarely you will find variable capacitor. So variable resistor is very famous. Okay, variable resistor is very famous. You have seen that rheostat is a very good example, which you have commonly seen in the laboratory as a variable resistor. But you will find that the variable capacitance and variable inductance are difficult to find as far as laboratory is concerned. If you have to use a variable capacitor or a variable inductor, then it should be restricted to some kind of application, specific application for that. Okay, so you see the ratings is written on the capacitor. So these types of capacitors are very famous, which we these capacitors are famous very famous capacitors. They are radial capacitors, electrolytic type, and as you can see, it is written that it is 35 volts and 1000 microfarad. Similarly, you can see that this is a capacitor of 100 microfarad. If you see properly, it is written here that it is 100 microfarad. If you point out this, whatever the wherever I am pointing, if you see uh, laser I will use this. This value is very very important. Before starting or using any other capacitor, you should see what is the capacitor rating. And rating, I mean that how much voltage it can support. That means 35 volt means that you can use this capacitor to have a voltage rating of up to 35 volts. That means it can maintain a constant voltage of 35 volt if used for DC applications. Similarly, you can see the sizes of this capacitor is small as compared to this, but its capacitance is 47 microfarad and 50 volt. So the radial wire they are calling because of these leads, this type of connection which you are getting. And yeah, these are all polarized capacitors. That means the value of plus and minus polarities are fixed. For example, if this is plus, it is indicated, not shown in this figure. But if it is plus, then this should be the minus, and always it should be connected like this. Never make a mistake of polarized capacitor to have a wrong connection, otherwise it will blow away. Okay, so these are very very famous, used in laboratory. We are also using these type of capacitors. As you can see in this figure, all these capacitors which are shown here are of this type. Okay, another very big capacitor, for example, if you are seeing the capacitance value, this is 39,000 microfarad, and but the voltage rating is small, that is 10 volts. So these are aluminum electrolytic capacitors with screw terminals. So these are the screw terminals which you are seeing. These are also very used in some specific applications. Okay, this is our circuit which I would like to show you, that built by our student. So this is a switch, this is the input side, all these are inductors. Okay, all these black ones are diode, this is switch, MOSFET, and all these blue one are resistor. And this board is known as a PCB board. The fabrication is first done, and then these components are fixed over it and soldered at the back side. Okay, so this is the, for example, another application. You can see C in capacitor. Why we are using C in capacitor? Because the input voltage which we are using here, uh, input voltage, this is the side for V in. Now the V in is a constant DC voltage, but it may fluctuate something like this. Now when we use in add some capacitor in parallel with this DC voltage, so what we get are smooth DC voltage. So that's why this input capacitance is used. This is also very famous application of capacitors, is to regulate the fluctuations in the constant DC supply to a straight one, and that's why we have used it in uh, this input capacitor, which is equally responsible for maintaining this input voltage as a constant. Okay, so this is one of the applications. And all these capacitors C1, C2, and C3 are boosting capacitors. That means this is boosting voltage for this circuit, and this is famous. This circuit is famously known as high gain boost circuit. Okay, so boost means that if you are supplying V in 12 volt, you can get 70 volt at the output. That means this is the output terminals which we have at the output. At the load side we can get up to 70 volts. So 70 volts, so this is known as high gain DC to DC circuits. Okay, all these another famous topology is axial style aluminum electrode. So why this axial? Because they don't have these type of structure leads, but rather than they are using this long wires, or you can say leads, or axial style. That means the connections are like this as shown in the figure. So this is axial style capacitor. As you can see, this is written, the value is written 100 microfarad and 150 volt DC, and that can be used up to this temperature. It is all written here. So these capacitors can also be used. it is easy to fix them because you are getting a comparatively long connection in the for the circuit. Okay, so similarly, we have seen for inductance. Similarly, we can also say for capacitance. This is a famous expression: I is equal to dq by dt, and q is cv. Okay, q is c into v, as we have seen earlier. So I will become C is constant, so it comes out. So I will become C times dV by dt. And by integrating this relationship, we can find that voltage is equal to 1 over C integral I dt. That means in the case of capacitance, the voltage is equal to the area under the I curve from minus infinity to t. That is the amount of voltage that the capacitor is going to get if the area under the I dt curve, I versus t curve is integrated and multiplied by 1 by c. Similarly, what we have seen in the case of inductor, we can find out the current I is equal to 1 over L integral v dt. Similarly, in the case of capacitance, we can find the voltage by integrating the area under the current curve. Okay, so that is this relation is the circuit point view of relation to get the voltage after integrating the current. So actually the expression, and if you are going to solve this numerical problem, then you will get this: V is equal to 1 over C 0 से लेके t I dt plus Vt naught. That is the initial capacitor voltage. So always you have to take into account the initial capacitor voltage before performing any numerical. If it is zero, then the expression will remain only V is equal to 1 over C from t naught to t. Generally we write 0 to infinity, but that is not always true. Sometimes we want only a specific time period, so we can write t naught to t. So this is the general expression for voltage, and I tell you that the integral expressions are the real world expressions. Why I am calling you real world expressions? Because every time in this world, whatever is being done is integrated. Okay, so voltage is the integration of area under the curve. So rarely there is any physical significance for derivation. Okay, physically I am talking about. Circuit point of view, you can say that uh, the I is equal to CV by dV by dt. That means the that is the current which is flowing into the system. Uh, so physically, this circuit point of view, this relation is correct. And but the important concept here is that this expression should be more realized, more it should be realized physically. For physical realization, this circuit expression should be used. Now, from this expression, you can have two things that, as we have seen in the case of inductor also, that the voltage कैन नॉट चेंज इन जीरो टाइम. ठीक है, तो जैसे हमने पहले पढ़ा था इंडक्टर के केस में कि द करंट कैन नॉट चेंज इन जीरो टाइम. सिमिलरली इन द केस ऑफ कैपेसिटर, दिस वोल्टेज कैन नॉट चेंज इन zero time. That means the abrupt change is not allowed. For example, if this is the voltage so of the capacitor which is increasing, okay, so this kind of abrupt change is not allowed in zero time. What will happen if there is an abrupt change in zero time? Very high current will flow through the terminals of the capacitors. Very high current will flow through the capacitor terminals of the through the capacitor, and eventually it will damage the capacitor. Similarly was the case with inductor. Whenever you are going to change the inductor current in instantaneously, then it is not going to work. So capacitor, by virtue of its design, is having a memory. Okay, from signals point you can say that this capacitor has a memory. Okay, and capacitor voltage cannot be changed instantaneously. So there are two important conclusions. One is that the capacitor is a memory having element having memory. Resistor don't have any memory. Why I'm saying resistor don't have any memory? Because the moment you change the current, you make the supply off through the resistor, it does not remember what is the last current it was flowing through it, or what was the last voltage through it. The moment you turn off your supply, everything goes to zero. But the capacitors and inductors, because they are energy storing elements, remember the last voltage which they have up charged upon. For example, once you have charged the capacitor through a switch and a small resistance, and even after that you open the switch, so the voltage will remain constant across its terminals. Okay, the voltage will remain constant till the point you get another circuit for discharging. Okay, so that means these capacitors and inductors, the capacitor remembers its past voltage value and inductor remembers its past current value. So this is a very important concept. This is a linear element with memory. Capacitors and inductors usually are linear elements having memory. Okay, and the famous expression for instantaneous energy stored in a capacitor in one of the cycles is half CV square. So you don't get confused that this energy will remain stored forever. It will only get stored in one of the cycles. For example, if you have a pulse of voltage and then you have gone at zero. So suppose you impressed a voltage upon a capacitor and then turned it to zero. So the voltage will remain, the energy will be stored at half CV square. So this energy will be stored half CV square, but if it is an AC circuit, then this energy will again return back to the source in the other cycle when the voltage across its terminals will change to negative, or the current flow direction flow changes. So instantaneously for DC circuits, the instantaneous energy which is stored in the system is half CV square. So capacitor, the stores energy. That is the basic concept we are dealing here with. So a capacitor is open circuit to DC. What do you mean by this? Uh, the capacitor is open circuit to DC. That means the capacitor, whenever you are going to charge a capacitor after charging, it acts like a open circuit. That means once you have charged the capacitor, the voltage will be available at its terminals, and so it becomes open circuit for a DC. So it gets charged to the maximum value through the voltage source, maximum value which is possible for DC circuits. For AC circuits, it charges up to the peak value of the sine wave. So the voltage on the capacitor must be continuous. Okay, so this is allowed. That means, as I have already shown you, that this kind of charging and discharging and discharging of capacitor is allowed because this is a continuous waveform, and this instantaneous operation is not allowed. That means we cannot change from V to zero in zero time. Okay, because this is zero time. If delta t approaches zero, if delta t approaches zero, according to the expression I is equal to C dV by dt, if uh, delta V approaches zero in zero time, practically the expression becomes indeterminate, and physically what happens that the current becomes very large and the capacitor can get damaged. Okay, so this is trivial to what we have seen in the case of inductances. Now the applications are important. For example, one of the applications is to get a pure DC voltage. Usually what happens that this DC voltage is not available in our laboratory. The DC voltage usually are available through different DC power supplies, 50 volt, 15 volt, 30 volt, 40 volt, or maximum 50 volts. That is also very rare. So what we do, we are interested in making, but AC is always available in our laboratory point of view, because the generation, transmission, and distribution are all AC. So AC is always available. DC is not available very frequently. So we use this AC circuit for rectifier. Rectifier means we are using diodes For rectification, okay, so what will it will become? It will become a wave like this. That means the negative part will be clipped away, and then with the help of capacitors, that is the smoothing operation, we can convert this waveform to a constant DC voltage as shown here. So this smoothing and regulation can be done with the help of a capacitor. Okay, so actually at the terminals, at the laboratory point, we are getting this AC wave, but we can make a DC wave from a AC wave. Okay, we can create a DC voltage with the help of capacitor, with the help of diodes and capacitor. So the capacitor plays very important role in smoothing down the waveform which is available. So in this case, this is also DC. This is its average value, but its ripple factor is very high. What do you mean by ripple factor? That is delta V is very high. So we are not interested in this kind of waveform. This is also DC and this is also DC, but we are not interested in this kind of waveform, half wave rectified waveform. Rather, we are interested in this kind of straight waveform, so that the constant voltage is DC. Okay, so usually if you have a DC supply directly, then you use in laboratory. Okay, and similarly, your SMPS, that is switch mode power supply, which is there in your computer systems, desktop, laptops, also use these DC to DC converters with a capacitor to have a constant voltage. Because in your laptop or desktop, you get different points for different DC voltages. One for floppy CD drive, another DC power for mouse, another DC power for another subsidiary devices. So we want different DC voltage levels, okay, at in our desktop as well as laptop. So these are always created through the regulated DC power supply. Regulated means the fluctuation should be plus minus zero point 0.1 volt if it is a 12-volt supply. So this is done through your uh, this is done through your capacitor as well as this diode rectifier bridge as plus capacitor. Because you see, it is when you plug your laptop or computer in a system, in your circuit which is available at your home, 3-point circuit or single phase supply. The single phase supply which is coming to your home is AC supply. Okay, or in your labs is mostly AC. So in labs we can have DC power supplies, or in house you can have a simple battery. Okay, so these are very small ratings. If we want to get large DC voltages, then we have to go for rectifier as well as capacitor uh, arrangement. So this is a very good example which I have taken from DiCarlo and Lin. They have used a current source. If you see, this is a current source. Okay, and they have just plotted it out. If I point it with this, so this is a current source and this is a capacitor. So the current source is changing like this. Okay, the current source is changing like this. So what you can do, you can write the expression of this straight line and integrate using this formula which we have already gone through. V is equal to 1 over C, 0 se leke t. So you can integration can be done from each cycle. That means we can integrate from 0 to 2, then we can integrate from 2 to 4. So whatever waveform will be there for 0 to 2, the similar will be is available for 2 to 4 and for so on. So the important thing which we are going to notice here, that the current is changing almost instantaneously from 2 to minus 2. That is allowed in the case of this capacitor. You see, the current is changing almost instantaneously from 2 to minus 2, but the voltage is uh, you can say is not changing instantaneously. So it is a half wave rectified sinusoidal waveform which we are getting as a voltage of capacitor. So it is quite strange that even the current is changing almost discontinuously at t is equal to 2, the voltage has remained continuous. So that is the property of capacitor. You cannot change the voltage uh, across the capacitor instantaneously, and that is not also happening. So whatever we are getting at 2 plus, the same voltage is there at 2 minus. Okay, and that is equal to 0 plus and 0 minus, which is equal to 0. So the current can change instantaneously through a capacitor, but the voltage cannot. So the voltage is continuous. The voltage has remained continuous. That is very, very important conclusion which we are drawn. And the shape of this voltage also tells you that this is a parabolic from this to this and this. Now, if you see, uh, the current is negative, the voltage is negative. Okay, the current is negative, the voltage is negative. Here, the current becomes positive. This the current becomes positive, but the voltage has remained negative. So what do you mean by this? This area is having a negative instantaneous power, and this area, I should use a different color. uh, this area is having some other positive power. So the instantaneous power can be find out by multiplying the instantaneous voltage and current. So here, since both are negative, so power is positive. That means the the power is positive. That means the capacitor, you can say that, you can take an analogy that capacitor is storing energy. And for this, if this is negative, voltage is negative and the current is positive, so you can say that this is having a negative power. So the average power in one cycle from 0 to 2 for the capacitor is also equal to 0. Okay, so instantaneously, capacitor is storing energy. In the other cycle, it is delivering this energy back to the current source. So all the average. So there are two conclusions from this example. The first conclusion is that the capacitor voltage is not changing instantaneously. It is half waves rectified sinusoidal with inverse polarity, negative polarity. And the third conclusion which you can draw is that the average power which is delivered to a capacitor in one complete cycle is zero. Okay. So So this I would like to tell you all these things. Now, whenever you go and purchase any, you can say at the mm, whenever you go and purchase in the market a capacitor, so how will you do that? So whenever you go and online purchase for a capacitor, so you have to look for two things. Suppose you want to use some capacitor in your laboratory experiments, then you have to go for then you have to first select the how much capacitance value you want. That is the first thing. And the second thing which you should always look for is the voltage rating, DC voltage rating. So as I am showing you, uh, the I'm sharing you how to purchase a capacitor if you go in a market. uh, so suppose this is the site which can be visible. I'm sure it is visible to you. Okay, so this is the site which is visible to you. So this is the name of the company, that is DG Key. Okay, so it is providing all these capacitors. So you can find that aluminum polymer capacitors are there, aluminum electrolytic capacitors are there, and film capacitors, mica capacitors, silicon capacitors. All these different types of capacitors are there. So for high capacitance value, and we use aluminum electrolytic capacitors which have a high charge holding capacity. So when you will go, you will find that this is the aluminum electrolytic capacitors, and It will ask you what kind of packaging you want. Okay, the capacitance is variable from zero point 0.1 microfarad to, you can say, you can drag it down to millifarad range. You can see the very large capacitors, 36,000 microfarad, 37,000 microfarad. Okay, so you can select, and then you can select the voltage ratings from 2.5 volt to 700 volt if this is available for that package. Okay, so all these things you can do for before selecting a capacitor. So suppose I want to buy a 55 microfarad capacitor. So I will click on this 55 microfarad capacitor, and then the voltage rating will be available. So all this are there. For example, these are all capacitors of different values. This is the manufacturer name. This is the capacitance value. For example, this is all 220 microfarad capacitance. This is the tolerance value. This is the voltage rating. Okay, so the voltage rating are different voltage rating. For example, 16 volt, 35 volt, 25 volt, 100 volt. For example, this is 47 microfarad, 100 volt general purpose capacitors, and all this is the this in the end you will find that it is radial or not. For example, this is if it is radial, it is surface mount. Okay, so all these things you have to look for before purchasing a capacitor. Once you have decided the capacitance value, and this is the ripple current ratings, usually polarization. So all these are polarized because we are using electrolytic capacitors. So all these are polar means all this is polarized. And then you can go for, when you click one model, that suppose I have to buy for this, then this becomes available to you, that this is this manufacturer name, manufacturer part. Okay, everything will come. And the most important thing is which is available. So you can specification, you can see that this is 47 microfarad, 50 volt. ESR they have not written. uh, you have to measure it in your lab at DC value, because ESR also changes for AC case with frequency. Okay, so once you have decided, then you can download this data sheet. Okay, once you have decided that I would like to buy this capacitor, then you buy this data sheet. So in data sheet everything is written. This is the voltage range, this is the rated capacitance, so, and how much losses are there, what is the stability, what is the structure, everything is given in the data sheet, and then you decide. Okay, so this is all from my side. uh, this is all from my side. We will discuss this class again later on. Thank you.